What you're looking at is my advanced games development project, Rogue AI. The game prototype is set in an abandoned facility where an overseer AI has gone rogue, deploying its drones and seekers to find and catch the trespassing player. The main focus of this video is breaking down the systems behind my game. I'll talk about how I built them using Unreal Engine's toolset, why I made certain technical decisions, and how well those decisions support the gameplay and the brief I was provided. The AI system is the core of this project and is easily the most complex part. There are two types of enemies in my game, each with a different purpose. First are the drones, which patrol along a fixed route, can spot the player and raise an alarm. Then there are the seekers, which are spawned in when the alarm is raised, and go to the location of the noise, searching for the player and chasing them if they are spotted. This double enemy setup is common in stealth and horror games. In Five Nights at Freddy's Security Breach, for example, staff bots patrol and raise alerts, while more dangerous enemies handle the actual pursuit. I like this kind of design because it gives the player room to make mistakes, but escalates the threat as a consequence, which fits well with the brief I was given. I coded this mechanic using Unreal Engine's behavior tree and blackboard system, along with the AI controllers and the AI perception component. It all starts with the AI controller. No, not the enemy itself. The controller is mainly used to possess each of the enemy instances and control their decision making. Think of it as the puppeteer, pulling the strings and deciding what will happen. The AI controller makes its decisions based on external input through the AI perception component. This component captures senses. Unreal provides a few by default, and the ones I implemented are sight, hearing, and damage senses. In simple terms, these are event-based signals that the AI will capture. This is much better than something like on-tick checks, and while I'm sure those work just as well, the event-based system will be much more performant over the other. Once the AI controller perceives one of these senses, the signal will run through my custom function that determines which sense was perceived, and send the signal to another function which handles the sense. Here I've got one for sight, hearing, and damage. This sort of decision making can be somewhat implemented using the enemy itself, or even the behavior trees. However, using the behavior trees for tasks and AI controllers for decisions ensures a separation of concerns between the systems. This avoids tight coupling as well as makes debugging easier. Speaking of behavior trees, they are a powerful way to create tasks and behaviors for your NPCs. Each tree starts at the root and runs downward, left to right. Yes, it would make more sense if it went up the tree, but this is Unreal Engine. Selector nodes decide which branch gets executed based on decorators, which are a way to add conditions in behavior trees. Kind of like an if statement or a switch case. In these decorators, you can also set them to abort a branch if things change mid-execution. I made use of subtrees too, which lets me reuse the same behavior logic in multiple places without having to set it up from scratch. This is one of the few ways I kept the code reusable and modular in my project. Now, we need a base enemy character. This one will house basic code implementations that will later be specialized using inheritance. The behavior tree runs general tasks, but it can also send a signal to the enemy and run the specialized pieces of code. I do this using interfaces. An interface allows me to communicate between blueprints without introducing tight coupling. What tight coupling creates is dependencies between blueprints. This makes your systems inflexible, fragile, and hard to scale. Interfaces can be messaged in an abstract way by any blueprint, and blueprints that implement that interface will receive the signal without knowing who sends it, while executing their own polymorphic implementation of it. This makes them an amazing solution to reducing coupling in your code. With everything in place now, the flow is simple. The AI perceives a sense, the AI controller decides what to do, and the behavior tree carries out tasks that drive the enemy. Separating decisions from actions made the logic easier to read, debug, and tweak whenever I wanted to adjust the AI's behavior. There is also the Environment Query System, EQS, which is Unreal's way of helping AI make smarter decisions based on the world around them. Instead of hard-coding search points, EQS runs queries to find the best locations based on a set of rules. I used EQS to handle searching once the player breaks line of sight. When the seeker loses the player, it runs a query around the last known location. It then scores valid points based on things like distance and line of sight, and feeds the best result back into the behavior tree through a blackboard. This makes the enemies feel like they are actively hunting the player instead of wandering around randomly, and it plugs in cleanly into the existing AI setup. This system is very flexible, which makes it a great choice for a number of applications, which is why I used the AQS system for other things such as random enemy wandering and enemy spawning. One important design choice was making sure the AI doesn't endlessly chase the player. Instead, I added a disengage where the seeker goes into a searching state after losing sight of the player. This supports stealth and recovery rather than turning every mistake into a fail state. It also keeps the AI logic cleaner and more predictable. But how do the drones spawn the seekers without tight coupling? This is where static classes come in, or more specifically, the game mode. I needed a way of sending data to a manager object which would take it and handle things from there. For this, I made an actor component called Seeker Manager and a new interface with a similar name. The component keeps track of a token count, which effectively limits how many seekers can be spawned. When a drone detects the player, it calls a spawn function through the interface, consumes the token, and spawns the seeker. If there are no tokens left, nothing spawns. I attached this component to the game mode, which acts as a static class. This means it is always loaded when the game mode is active, without needing to place any blueprints manually in the level. This setup stays modular, avoids tight coupling, and remains flexible even if the game mode changes later on. The documentation here was my source, as it details that the game mode acts like a static class, but the difference is that it doesn't persist in all the levels. Static classes are nice to use as mediators between systems. This is because they are always loaded and you don't need 20 mediators in your level. However, it could become very troublesome when you've got this big god mediator blueprint. That is why my approach works best here, because I compartmentalize all the mediators into their own components and attach them to only one static class. Another thing the enemy is capable of is noise detection. As mentioned previously, I set up a hearing sense and allowed the Seeker AI to hear sounds. The drone doesn't have this, as it is supposed to patrol and respond to sight and damage only. When a noise event happens, it updates the point of interest value on the blackboard, which then influences the tasks in the behavior tree. For example, when the drone signals the alarm, the Seeker spawns. It will then hear the noise and go investigate. Originally, the player's footsteps also made noise events, but I decided to disable that and only leave it on when the player lands after jumping. This felt more natural and fair for the player, as they won't get confused by why they are getting detected. So the AI reacts to what the player does, which from a design perspective adds depth to the stealth gameplay and encourages the player to think more carefully about how they move through the space. If I had to improve one thing here, I would add more verticality to the level, and encourage the player to jump more often. That would add more tension, since it's the only way the player makes noise. Okay, let's move on from all that head-aching AI stuff and talk about something simpler. Doors. Access to new areas is controlled through locked doors. Keycards are required to open these locked doors. This is a very simple concept in video games dubbed the lock and key puzzle. In my setup, I have a terminal that controls the door remotely. To handle interaction cleanly, I used Unreal interfaces again. Any object the player can interact with, whether it's a door, keycard, or a terminal, implements the same interaction interface. That means the player character doesn't need to know what it's interacting with, only that it can interact. The doors themselves only contain logic for opening and closing using a timeline. The terminal is the one responsible for querying the inventory component of the actor that interacts with it, and checking the security level, then sends a message through another interface to any door, light, or anything else that subscribes and listens to the door's message. This approach takes more setup at the start, but scales much better. If I wanted to add a new door type or any new access conditions later, I wouldn't need to rewrite the existing logic, which is the kind of modularity that is really important in scalable projects. To improve on this even more, I could encapsulate the security level check into its own component, which would let me add it to other things that might not necessarily be a terminal, such as a computer, without having to rewrite the same code. Now, before I jump into the inventory, it's important to mention that the items that go into the inventory are data assets, which are a customizable way to store multiple different variable types. My data assets store things like the name and the description, as well as things like the model and the sprite of the item. I separate the key items from the normal items using a boolean, which is also stored here. With this setup, I only need to place a generic item into the level and choose what I want it to be from a dropdown. I will have a simple way to distribute items on the level. Okay, but with that out of the way, it's time to talk about the inventory system. The inventory is made into a component which can be attached to any character class. It is used to store keycards and other important items such as the flashlight. It's set up as a data-driven system rather than a hard-coded one, which makes it flexible and easy to expand. The way it works is that when the player interacts with an item, using an interface, the item will query the interacting actor, in this case the player, and check if they have an inventory. Only if the interacting actor has an inventory will the item be added to the inventory component. This is a way of validating that the actor can actually pick up the item and prevents any possible bugs from happening in the system. Now, UI updates, just like the keycard collection from the inventory, are handled using event-based functions. So instead of the UI constantly checking the inventory state, it listens for specific events and only updates when something changes. This keeps the UI logic clean and efficient. As for the design of the UI, I went with a dual inventory approach. On the left are the key items that the player finds, and on the right are the consumables and other such items. This approach keeps the player informed without having to sort through irrelevant items. This is also why I added a third panel in the inventory for displaying the information of the item you hover over. This was, once again, accomplished by sending information through interface calls. It's quite handy and only took me like a few days to figure out. Couldn't say the same for the designer part of the UI. Across the whole project, I focused heavily on modular architecture and following object-oriented programming principles. Actor components handle self-contained functionality. Interfaces define how systems communicate, and are the sole reason I didn't need to resort to casting. And event dispatchers manage more coupled messaging. This means most of the systems don't know about each other directly, which reduces dependencies and makes the project easier to work on. The only trade-off here is that the event-driven systems can be harder to debug, especially when you have multiple modular pieces reacting to the same event. But the benefit is that the codebase is much more flexible and maintainable overall. Before I wrap things up, I've got to mention my Footsteps actor component. It attaches to any character class and plays customizable audio cues based on the physical material of the floor. The system uses structs to bundle audio for different movement speeds and landing events, giving you a clean and simple way to assign sounds to materials and movement states. The component is fully drag and drop with no extra setup required, and in the future I plan to expand it to drive audio directly from animations instead of the character speed. In game, it is currently used by both the player and the seeker enemies. It's important to mention that the player character communicates with the Footsteps component using event dispatchers. With an onFootstep call, the player subscribes to that call and fires off the make noise event when it is triggered. Event dispatchers are great when you have an object listening in for an event to fire off without having the other object coupled to anything. A great resource for event dispatchers, as well as the aforementioned interfaces, is this YouTube video by Ali El-Zahiri, which details and demonstrates the use cases for both. Overall, the tools and techniques I used were well established within the industry and were a strong fit for both the brief and the experience I wanted to create. The tools and event-driven systems I used are commonly seen in professional workflows, and they allowed me to build reactive, stealth-focused gameplay without relying on tightly coupled logic or constant tick-based checks. The modular structure reflects how AI systems are typically built in larger projects. While it can make debugging a bit more involved, it keeps the project flexible, scalable, and easier to expand over time. The decisions I made directly support clean system architecture, responsive AI behavior, and maintainable code, making them a strong fit for both the scenario and the technical requirements of the brief. Thank you for watching, and I hope you enjoyed seeing the breakdown of my work.